All right, now it's working. Welcome. It is, what is today? Today's Thursday. Oh my gosh, I'm forgetting what day it is. It just feels like the same day over and over again. Wake up, go to my computer, start streaming, work on videos, upload stuff, and then the cycle repeats. Oh my god, no, there are. Um, yeah, I think when you first open Twitch, when you first click on a link in Twitch, they give you an ad. But there should not be any ads after that, right? Uh, at least I think so. Yeah, there should not be any ads after that. There should only be one ad. Yeah, so they start the aftermath. Yeah, good job. You're reading the title. It's the aftermath after the quiz yesterday. Yes. Why is it the aftermath? That's why. So today we'll go over. I don't want to start our new unit yet. I'll start the circuit stuff tomorrow, but we'll kind of ease into it. I don't want to jump straight into the next unit, um, and we'll talk about the project that is. We'll try our best to do this project because we need some more test points in our test category, right? So we'll see how much we can do on our own, and then hopefully once we return to school in May, then we can use the resources at school to finish off the project. Otherwise, you may have to do the project on your own. All right. That being said, let's go and take a look at all of those questions. We did all right. Here, let me pull up some stats for you. Some of you like stats. But I thought we could do a little better. Here's some stats. Here's some stats. Someone did get 100. Of course, someone gets 100. Ruins the whole curve. But our average was 65%, which is, not bad. It's almost like a college class now. Usually in colleges, you'll see averages of somewhere around the 60s. Um, yeah, and most of you took, your average time was around 25 minutes. So most of you used up your time. So that was good. So let's go through the questions. Now remember, it was kind of randomized, so not everyone got the exact same questions. Um, that way, it's a little fresh for everyone. How's the curve going to be? What curve? What are you talking about? When are we going back? Well, they're going to vote on it today. Currently, it is after spring break. However, there's a board meeting today that may extend it because LAUSD is, first week of May. So usually we kind of copy what LAUSD does. So we'll just most likely going to copy what they do. Therefore, most likely it may be the first week of May. Yeah. Please curve it. I might, maybe like 3 points at most if I feel like it, but we'll see. We'll see. So here's question one. It says a charged balloon can attract and attach to a neutral wall. This is the thing that I did with you guys at school. So how do you attract things that are neutral? Well, you have to polarize it. That means to shift the electrons around. Now, if it's an insulating material, the electrons will shift within the atom. So the front side, if you bring your balloon, which is negative, if you bring your balloon close to the wall, the front side of the wall will become positive as the electrons in the front will be shifted inwards to the other side of the atom. Of course, if it's a conductive material, it will actually, move the electrons from atom to atom, so it's actually, much further away than the front. But that's we don't need a conductive material to attract things. We can actually attract to neutral insulating type material as well. 44% of you got polarization. Ooh. Coulomb's law is a statement of the force of attraction or repulsion between two charges. It is called an inverse square law, like gravity. The inverse square law is all about the denominator of your formula. You'll see that it is an r squared in the denominator, which for both of them, one of them is gmm over r squared, the other is kqq over r squared. So the electric force decreases rapidly. That's because it's 1 over r squared, so as r gets bigger, your fraction gets smaller really quickly. Okay. 86%, so that one we did pretty well. This one we did not do so well. Yikes. The forces are unequal. That can't be. As you might have noticed, there's always one Newton's third law question in all of our tests in some way or fashion. So Newton's third law is, forces are equal but opposite in direction. Yeah, that's it. So whether it's the electrostatic force between charges or gravitational force between masses, you're going to have forces that are equal in magnitude but opposite in direction. The Earth pulls the moon just as hard as the moon pulls the Earth. You can say the same thing about yourself. You pull the Earth upwards just as hard as the Earth pulls you downwards. Yeah. So just remember, Newton's third law applies to everything. Next one. The strength of the force on a charge in an electric field depends on... Okay, we're talking about the strength, which means the magnitude. The magnitude of E must be the magnitude of F must be based on the magnitude of Q and the magnitude of E, because F equals EQ, or QE. Right? The direction will tell you the direction, but that's not what the question is about. Since we want to know about the force, or the strength of the force, we want to focus on the magnitudes of both values, both variables. The charge on one proton is the elementary charge, 1.6 times 10 to the negative 19 coulombs. How many protons? This is they're giving you the total charge. The total charge is 1 coulomb. And if each proton is 1.6 times 10 to the negative 19, how many protons does it take to make 1? Well, it's just total divided by the individual charge. 1 divided by 1.6 e negative 19. Or just the inverse of it. This is just like the thing you have in your flippy. It said 1 coulomb of, or negative 1 coulomb of charge. How many electrons is it? Well, it's just 1 divided by the charge of 1 electron. So in this case, it's 1 divided by the charge of 1 proton, which is the same. It's the same. So if you had negative 1 coulomb, it would be the same number of electrons. The direction of an electric field is, the electric field is a vector. Since F equals QE, Q is a scalar. The direction of the field must be the direction of the force. And this is the force on a small positive test charge. This was on our quiz poll, or Kahoot, wasn't it? This was a Kahoot question. A uniform electric field is where it's all constant. And of course the direction has to be the same, the magnitude has to be the same. That's what uniform means. Uniform is not something you wear every day, the same thing over and over again. But it just means constant. And so the direction cannot change and the magnitude cannot change. And most of you got it, 84%. Wow, very good. Do we have 100 anywhere? I don't know if we have 100 anywhere. We'll find out. Point P is 0.50. This is actually from your worksheets. So if you did your worksheet, you did pretty well on this one. The intensity of the electric field, that's KQ over R squared. And that's all there is to it. KQ over R squared. Next one. An electron traveling at constant speed from south to... Oh, this one was a little tricky, it seems. Okay, so let's read through this. It says, an electron traveling at constant speed from south to north. Okay, so imagine, going from San Diego upwards towards San Francisco or something. South to north. I don't know. I guess that's kind of diagonal a little bit. In any case, South Pole to North Pole, so you're going upwards. Not upwards, I shouldn't say upwards. Upwards would technically mean upwards to the sky. Okay? When you say north, south, east, west, that's on the plane of the ground. So you're going towards the north, and then enters a region where there's a uniform electric field that is directed toward the south. So the electron is trying to go northward while there's a field that points southward against its motion. So what kind of force does an electron feel? Well, electrons are like salmon, remember? They're like salmon. They go up the waterfall during migration. So since the electric field is in the opposite direction, electrons like that, they'll actually accelerate further towards the north. So the force must be in the opposite direction to the electric field. If the electric field is south, then the force must be north. All right. At what separation distance will two charges, each of magnitude 6, and exert a force 1 newtons on each other? Again, this is straight from the worksheets. Make sure you do those. It's even the exact same numbers, so no excuses. I guess the trick, or to force you to do all this stuff, is to put some of the questions on your tests and quizzes. Aha! So the only way to be prepared is to do them all. Yay! At what separation distance will two charges, each of magnitude 6 microcoulombs, which is 6 times 10 to the negative 6, exert a force of 1.4. So F is given, Q is given. Q is the same for both, so you can do Q times Q, which is Q squared. And you're just solving for R. So you have to isolate R. Isolate. So if F is equal to, F is equal to K, Q1, Q2, but Q1 and Q2 are the same. We can rewrite this as K. Q times Q is Q squared over R squared. Solving for R gives us, we'll do the old swapperoonie, and then square root both sides. So there you have it, the square root of KQ squared over the force. Right? And that's about it. And it's just plug and chug. Alright. What is the electric field strength at a point in space where 5.2 e negative 6 Coulomb charged object experiences an electric force? I see most of you got this. Just it's the other equation. K force is equal to EQ, and so it's just force divided by charge. You just take the two numbers, divide them. And I strategically made sure to put answer choices where you do the operation incorrectly. So for example, if you did charge divided by force or something, just look at the units. I mean, you know that the electric field is in newtons per coulombs, right? So that's force divided by charge. Newtons, which is force, coulombs is charge. Then units kind of tell you what you should be doing. Which statement about electric field lines is false? Actually, most of you got this. Lines that are close together indicate weak field, and lines that are apart indicate strong. Yeah, that's the opposite of what is true. When you have high concentration or high number of lines in a region, that means it's very strong. And then if they are spread apart and further apart, then it means it is weak. So most of you got that. That was good. This one. This one's one of the harder questions. Yeah, I had a category where it's like hard questions, and you choose 2 out of the hard questions. This one being one of them. Notice how in this picture it says the figure demonstrates charging by. In this picture, the charged object doesn't actually touch the other object, so there's no contact between them. You're just near it. There's a space between them, and then once you come near it, you shift away the charges. If you bring a positive object close to an insulator, it's going to shift the charges such that the positive charges go to the back now, and the electrons, or the negative charges, get pulled to the face. It's kind of like the opposite of what we're doing with the balloon and the wall. Again, this is polarization. It's a temporary shift. We're not actually charging it through induction. I know why most people picked induction. It's because there's this word induced in there, and so it's kind of misleading. We are inducing the separation of charges, but the separation of charges is the definition for polarization. Polarization. All right. This is, again, straight from your worksheet, so make sure you do your worksheet. More of you got it. Some of you missed it. These are vectors, so you can't just add the vectors that are in, one in the y-axis, one in the x-axis. You have to use the Pythagorean theorem. So you have to find the individual forces. So these are all the things we've done so many times. Let's do ocean here, and then we'll do orange here. Okay, so how do we do this? Well, I have to find the force between each pair. Okay, they're all positive charges, so if this is positive, if this is positive, this is positive, look at the numbers, they're all positive. Okay, there's a force that pushes x to the right from the ocean colored one, and there's a force that pushes x upwards from the orange one. And so we add these two vectors. How do we add them? Well, one tip to tail method. So to the right and up means going up to the right, upright. We want this upright vector. And so by finding the individual vectors, go ahead and use the Pythagorean theorem. And if you notice that it is patterned, then you can do it easily. Let's see, what are the values? 3, 4, and the distance is 0.6, and then the other one is 4 and 4. Okay, so this is k times 3e negative 6 times times 4 e negative 6 divided by 0.6 squared. This one up here would be k times 4 e negative 6 times 4 e negative 6 divided by 0.6 squared. Okay? And then once you find these values, let's call this force 1, force 2. Once you find these two values, you have to take the Pythagorean theorem of it, force 1 squared plus force 2 squared. Technically, this is the x, sigma fx, sigma fy. Remember all that stuff? Yeah. All right. A positive charge on an object means that the object possesses... Oh, wow, we got 100? Oh, my gosh. Hey, can we start a 100 hype train? Let's do it. 100 hype train. A positive charge on an object means that the object possesses more protons than electrons. Yay, there it is, 100. Everyone got it, yes. Okay, cool. Next one. A material in which charges cannot move freely is called Chapito with the emotes. A material in which charges cannot move freely. Yeah, that's an insulator. This is straight definition stuff. Insulating materials don't let your charges move around. 99 plus 1 for Kuya Casey. Thanks Casey for the extra information. What is the electric field strength at a point in space where an electron experiences an initial acceleration of blah 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 meters per second squared? The mass is given. So this is another question that is from your worksheet. Okay, they're giving you acceleration and the mass, and we want to find the field. Wow. So this is a two-step process in that first you have to find the force, and to do that we use FOMA, Newton's second law. F equals ma. So the mass of the electron times the acceleration of the electron will give you the force. And we also know that the force is equal to the field times the charge. F equals EQ or QE, doesn't matter which way you write it. My eraser is not working. Oh, there we go. there it is. And once you have mass times acceleration, then set that equal to EQ. So mass times acceleration has to equal EQ. And so the electric field is mass times acceleration divided by the charge. And this is an electron, so the charge of an electron. All right. And we just want the strength, and remember this word strength is another word for the term magnitude, right? So we just want the magnitude of the value, no direction. A potential difference is defined as electrical potential energy per charge. An informal name for potential difference is voltage. Yes, even if you didn't know, you could kind of use process of elimination and just get through all of this, right? Capacitance is the last flippy entry we did. Remember, it's the ability to hold charge, so it has nothing to do with potential differences. Energy, how could it be energy if the potential difference is energy per charge? So if something is energy per coulombs or joules per coulomb, it's not going to be equal to joules, right? So it can't be energy. And now you're between voltage and current. Current is a flow of charges, which we'll dig into next unit. Of course, you're down to 50-50, and perhaps it's a term that you actually learned about this unit, right? So use process of elimination wherever possible if you're unsure. Logic it out. The magnitude of the electric field near a point charge. Okay, we did pretty well here. Decreases in strength as distance from the charges. It's an R² function, so the further away you are, the weaker it is. That's a freebie. Here we go. Slightly more challenging. The picture shows the electric field lines for two charges a short distance apart. Okay, so you can see how there is a vertical asymptote in the middle, which will tell you that they're the same, or just the fact that the arrows are pointing inwards. If arrows are pointing inwards, that means they are two negative charges. It looks difficult, but it's actually really easy, right? Remember, the electric field goes away from positive, but towards negative. And you can see how all of the arrows are towards, so it's all negative. After a balloon is rubbed against your hair, yes, the balloon will steal your electrons. The balloon will become negative, leaving your hair positive. But the answer is that the combined charges of the two is actually still zero. Whatever your hair lost was gained by the balloon. So if you add balloon and hair together, it's still zero. It's neutral. This one was a tricky one. A banana peel. The balloon becomes positive. Nope, balloon is negative. The balloon is repelled by the hair. No, remember, if you bring the balloon close to the hair, it attracts the hair, and we were able to move. Someone say, I don't know who we did it in first period. Actually, I don't remember any of them. I know we did someone's hair. Your hair becomes negatively charged, and so it will actually that's actually false. The balloon becomes negative. Oh yeah, Maddie, we used Maddie's hair. Thanks, Maddie, for donating your hair to science temporarily. Yeah. All right. When placed on a conductor, charges of the same kind spread out over the surface of the conductor. Yes. So remember, conductors allow your charges to move freely, so they will spread out. This is the little Harry Potter wand and the snowflake thing that I had that floats around. Remember, as soon as it touched the magic wand, it started repelling the wand because they're both the same. Not only that, instead of being a crumpled up little piece of paper, it kind of inflated itself as the charges spread out. Right? So use all of the demos and all the life experiences you had to logic these questions out. Electric field has units of newtons per coulomb and over C equivalent units. Whoa, another 100? Yes, let's get another 100. Basically, if you did the lab, right, and when you're measuring things, you can see how it says it in V/m, volts per meter. Yeah, 100. And you could also get this from the VED equation, V equals ED. Remember, the voltage is equal to the constant electric field times the distance separating the two plates or whatever. So voltage divided by distance gives you E, right? Chapito B, number 1. Yes. All right. What happens to electric charge when it is neutralized? This one we didn't do so well. Remember, charge cannot be created or destroyed. At least, I'll put that with an asterisk. At least for the most part, it cannot be created or destroyed. There are things called virtual charges that come into existence and then leave our universe over and over again. But those are special topics. If you'd like to learn more, consider getting a PhD in physics, because this is not even taught in AP. So anyway, charges cannot be created or destroyed. When you neutralize, that just means that the total sum is neutralized. The total amount of protons now equal the total amount of electrons, so that the net charge is 0. Now, you don't actually have to have 100% neutralization. You can have partial neutralization. So when a +2 and a -1 neutralize each other, the total is just 2 minus 1, which is just 1. So in essence, they're all still there. It's just the net value is different. Protons and electrons form neutrally charged atoms and molecules. Okay, they don't disappear. What you might be thinking of is annihilation, which is not neutralization. Annihilation is different. Annihilation is where a matter particle like proton crashes into an antimatter-like particle, the antimatter of that particle. So the antimatter of electron would be a positron. And so when an electron and a positron combine, they annihilate each other, turning into pure energy, gluons. So annihilation is different than actual neutralization. Here we go. We're almost done, actually. A conducting sphere. This one definitely challenging. This is probably one of the more challenging questions on the quiz. So let's take a look. A conducting sphere has a net charge. Actually, no, not this one. This one's easy. I was thinking of a different one. A conducting sphere has a net charge of blah, blah, blah. What is the approximate number of excess electrons? This is just total charge divided by a single electron. So the total charge is given, divided by the charge of one electron. What's the charge of one electron? Chat, what is the charge of one electron? Ooh, who's going to be first? Let's see. I think there's a 3-second delay, and then the time to think. So any time now. Charge of one electron is the elementary charge. Well, it's -1 what? It's -1 E. So let's go ahead and multiply Speedy Cat's answer with Christian Tran's answer. So the charge of one electron is -1.6 times 10 to the -19. Okay. Yes, I know you've learned like +1 and -1 in chemistry, but it's +1 E, and E is 1.6 E -19. So it's -1.6 times 10 to the -19 coulombs. All right, so it's just total divided by single charge. Right, you have a bunch of bag of marbles, and if you know the mass of one marble, if you divide the total by the single, then you know how many marbles you have in your bag. Yay! Next one. Oops. A capacitor is 2 times 10 to the -6 coulombs. This is the only capacitor question we got, and we didn't do so well on this one. If you recall, the last thing we wrote for capacitors, the charge Q on any plate is equal to the capacitance C times the voltage V. Right. So all we're looking for is, well, actually, what we're doing is finding the difference or the change. If V is doubled, what happens to the charge? Okay. This C is the ability to hold a charge. So this is based on material properties, so it doesn't change. Okay, to change the capacitance, you have to actually change the capacitor itself. Kind of like the spring constant K is dependent on the spring itself, so you can't get a new K value, you have to change the spring. This doesn't change. So if you double V, if V goes up 2 times, then Q has to go up 2 times. That's all. That's all it is. You double V, you double the charge. Simple as that. 2 conductive spheres. Ah, yes. This is the question I was thinking of. The actual difficult one. The really difficult one, I should say. The 2 conductive spheres are charged to +3 and -q. Okay, and they're d apart. The force is F. Okay, now we're going to change it. Well, before we read the next part, let's go and define what F is. This is the 2 charges are separated, so this is Coulomb's law or Coulomb's equation here. F is equal to K times Q over R squared. Now, what are our variables? 3Q and -Q with a separation of D. So that would be K times 3Q times 1Q. Remember, we only plug in positive charges because it's the absolute value. Divided by D squared. This gives us 3K Q squared over D squared. Alright, now for the next part. It says the spheres are connected momentarily by a wire. If you connect conductive spheres with a wire, the wire will allow the charges to flow. This is the neutralization part. This is how it happens. The charges can now flow from one ball or one conductive sphere to the next, and they neutralize each other. What is neutralization? Well, it just means to add them up. But once you take the wire away, then the charges will split up. So originally we had +3 and -1. Okay. Once you connect them, you neutralize, so they combine to form +2. And then if you break it, then they'll split up evenly. This +2 will split up so that it's 1Q and 1Q. Okay? So the question is, what is this new force? Well, if you're 1Q and 1Q, then force is equal to K times 1 is Q squared divided by the same distance, D squared. Alright, now we compare. The original one was 3KQ squared over D squared. The new one, we'll call this new, F new. The new one is 1 times KQ squared over D squared. So it's 3 times smaller. And so it's F over 3. Yeah, that one was definitely challenging. We're almost done. Here we go. Oh no, this one we did not do so well. Maybe it's because it has too many options. As I increase the number of options, it decreases your ability to guess, right? So I guess I'm going to have like 50 different multiple choice possibilities. That way you can't just guess it. What is this question? The figure below shows 2 particles, each with charge of +Q, at the corners of a square. What is the direction of the net electric field? Okay, so this is an electric field equation question, similar to one we did in class, right? What you want to do, again, use the strategies. Color them or something, color code them. We have blue here, and we have, let's use orange. We have orange here, and what we want to do is find the E at this corner here. Okay, both of them are positive. Blue is positive, orange is positive. So we'll do it one at a time. What is the electric field from the blue charge at this point? Well, the electric field is going to be away from the positive. So if we're going away from blue, then away would be downwards this way. Okay. Next, we'll do the orange one. If we have another positive charge, okay, what is the electric field from this positive charge? Well, it is away from the positive charge, and to move away from orange, we have to go left. So it's away this way, E2. And now we want to find the total. Similar to the other Pythagorean theorem problem we had, you have to do Pythagorean theorem for these two. Now the distance is the same and the value is the same. So if the distance is the same, the value is the same, then KQ over R squared is going to give you the same number, right? I know the distance is the same because it's a square. So all of the distances are the same. And the charges are the same. So E must be the same value, except one is in the y-axis, the other is in the x-axis. Okay, if you're going downwards and to the left equal amounts, then what is your net vector? Well, your net vector must be diagonal to the left, downwards to the left. And how many degrees is this? Pew. This is 225 degrees. 180 plus the 45. All right. I guess that's it. That's the end. We didn't do too bad. It will be curved by 3 points. 3 points only. But still better than nothing. So your grade will be going up slightly. All right. So it should be on Aries. It'll be out of 27 instead of 30. On Canvas, it'll say 30. Alrighty then. So again, we're moving on to circuits, right? We have our Q3 project coming up. Today we just want to, set it in motion. Basically, quarter 3 project is the electric shoebox project. I'll give you the actual directions after we learn what circuits are and how to actually build circuits. But for now, you should be able to start, gather materials or something. Electric shoebox. Okay, so your assignment is actually just to find the box itself. Find a shoebox. Now, if you don't have a shoebox, that's fine. You can use any kind of box, really, as long as it's the size of a shoebox. Amazon boxes are fine, technically. Or you could just make it out of cardboard. You can make your own box. Can we have partners? Yeah, this is a project, so remember it's a solo or duo. So all of our quarterly projects are solo or duo. 100 points. 100. Test points. Okay. Now you don't get 100 points just for the box. Obviously, we have to do something with the box. We're going to design a scenery inside it. Typically this is inspired by like those electric doll houses. But you can actually do anything. You can even think outside the box. Use the box to create something. I've had students who like kind of change the entire thing, where they use their box to make like a car or make a the Star Trek Enterprise, and they actually built a spaceship. But the ultimate goal is to actually build a circuit inside that is powered by batteries, and you have like little switches, and those switches will turn on lights. The lights will function as a thematic element, meaning if let's say you did like the Starship Enterprise or whatever, right? This person used their lights as the thrusters, so you can actually hit the switch and then turn on the lights, and the red lights or whatever in the back look like the spaceship is firing its thrusters. So that's one way. Or if you're thinking inside the box, you could do like a camping scene, and let's say you have like a little campfire with people roasting marshmallows. You put a little LED in there and some red paper or whatever. You can use that as like a fire or something. But anyway, the actual details I will give you later. Just have in mind that you need a shoebox or something that is the size of a shoebox. Your goal is to find the box, find materials, or make a box, and start brainstorming. Brainstorm what theme you will use. And of course, think of who you want to work with. Who do you want to work with? Okay. You can choose anyone in honors physics, so anyone in periods 1, 5, or 6. Or you could do it by yourself, that's fine too. If you like working solo and it's easier for you. Obviously, it's going to be harder to do it over this, COVID-19 quarantine thing. We'll try to do as much as we can independently. Okay. I'll just continue to shift the due date over and over as far back as we can. But once we return to school, we can start using the resources at school, and then we'll have some time before we have to actually turn it in. If we do come back in May, for the most part, all we're going to do is our projects. We have our rocket project, we have our shoebox project, and then we'll just study for the final, really, after our circuits unit. Shift to end of May. Well, no, we still have our rocket project, so I want to get as many projects in our gradebook as possible. That way it will balance out all the tests. Yeah. Well, that's the ideal plan, Dennis. If we have that time in May, if we have all of May, then we can easily do it. If we don't return, then the final is the only thing that's going in, and that's rough. That's an oof. So my current plan is, if we return in May, we're just going to continue to work on our projects. We'll learn, we'll use more of our 3D printing. You can use the 3D printers for like design elements of your projects. When do we have a rocket project? Well, the rocket project is the end of the year, so that's like the last 2 weeks of May. And then we fire the rockets off in our softball, in the girls' softball field, at an angle, and then we measure like how far it goes. Typically, it goes like the whole field, and if you do everything right, man, these things fly really far. All right, so we went over our quiz today, right? And your assignment for now is to just find this shoebox. Okay, and think about who you want to work with. It's an electric shoebox, so you'll be doing some circuitry, attaching little LEDs and light bulbs to batteries. So there is some technical element to this. The actual assignment, like the type of circuit and all that stuff, all that minor, or not, I shouldn't say minor, all the more advanced directions will be given after we learn circuits. But for now, just find your box and find your partner, and perhaps even think about a theme that you want to design. So if it's a dollhouse, if it's a kitchen scene, if it's a living room scene, if it's a campfire scene, or if it's like Starry Night and you want to use light bulbs as the stars, or if it's a supernova, I don't know, it could be anything. If it's the one thing that I don't want to see is streetlights, because I always get that every year. Basically, students just use 3 light bulbs. It's a street light, red, yellow, and green, and they have a little car, and they're waiting for the right light to turn red or something, or to turn green. But anyway, that is all. Well, thank you for tuning in. We will start doing a little bit of circuit stuff tomorrow. So I will see you tomorrow. Bye.